Alright guys, we're on. We're talking about squeeze theorem today. So a squeeze theorem, what happens is that we're talking about some strategies to evaluate limits. So if f of x, g of x, and f of x are functions, and there's a picture right here that if g of x is in between, so I'm going to draw you a sketch right now. I might have to switch a marker in the next video, I probably will. So that looks like a pterodactyl, and then you have this, okay, and you have this, right? So here's h of x, okay, here's f of x, and in between here we have g of x. Let me move out of the way to make sure you can see that. So h of x is the pterodactyl, this is the parabola type thing, and this is g of x in between. So let's say that f of x is bounding g of x along with h of x. Okay? Let's say that's the case. So if there's some a value right here, some a value, right? We're going to say the limit as x approaches a of f of x equals L. Okay? Which would equal the limit of h of x as x approaches a. Which is also equal, because they're equal, that means whatever's in between has to also equal that limit, which equals limit of g of x as x approaches a, essentially. So, as the graph indicates, we just need to find the limits around g of x to solve for what the limit of g of x is at x equals a. So the theorem is very useful for calculating limits involving sine and cosine usually. Usually used for sine and cos. Okay? So if you know the limit of this, and that's in between, then you know the limit of g of x. It's whatever the limit of those two are. That's because sine and cosine are bound. You learned that in grade 11, that sine x is bound between negative 1 and 1, right? Sine x is bound between that. And then negative 1, that's also bound for cos x as well, right? Those two, they're bound by negative 1 and 1. So let's look at an example right here. You have so if you have like a limit as x approaches infinity of sine x over x squared, okay? We know that sine x is bound between negative 1 and 1, okay? So what can I do is divide both sides by x squared. So let's say that means if this is f of x, this is g of x, whatever's in between, this is h of x, right? So we're just lining them up. This is f of x, this is g of x, this is h of x, right? So what's the limit as x approaches infinity of minus 1 over x squared equals 0? Because as you get a huge number on the denominator, the whole fraction becomes 0. But that also equals a limit as x approaches infinity from 1 over x squared, which also equals 0. That proves that the limit, indeed, as x approaches infinity of sine x over x squared also equals 0. Okay. So using the squeeze theorem, we solve that problem right there. Now we talk about the topic of continuity. Okay? That's what you learn in usually grade 12 calculus, continuity. Okay. So, continuity. So what happens is that a function is continuous if its graph, if we can draw its graph, if we can draw its graph, okay, without removing pen to paper. So you can just draw it without lifting your hand off the page. It's gonna be continuous. So pen to paper. So this is continuous, right? Watch me draw this one. Whoa, that's continuous. Alright, whoop, alright. This one, no. Let me show you. Look, I took my hand off the board. Oh, not continuous. Okay? That's continuous. That's not continuous. Okay? So, if that's the case, let's talk about formalities here. So, formally, a function f of x is continuous. Make sure you guys get this down in your notes. It's continuous if f of a exists. Okay, that's the first one. F of a exists. Okay. Second one is a limit as x approaches a of f of x exists. Okay. And the limit as x approaches a of f of x equals f of a. Yay! Okay? That's how you know. It's continuous. F of a exists, the limit of f of x as x approaches a exists, limit as x approaches a of f of x equals f of a. Or you can just write what covers all these is the limit as x approaches a of f of x equals f of a. Okay? Long lecture, but we're going to get through it, team. Don't you worry. Got you covered over her. So, this is fine and dandy, but if I is an interval that f is continuous, on I, it's continuous at each point of I. So if you have I, this interval, right? Square, remember that square means including A and B. Okay. Then the limit as x approaches a from the right, okay, of f of x has to equal f of a, and the limit as x approaches b from the left, f of x is f of b. Okay. So those are two statements right there. So polynomials, logarithms, exponentials, sine, and cosine are all continuous functions. So let's write that down for the road. Polynomials, all right, logs, exponentials, sine / cosine x are continuous functions. Okay. Polynomials, logs, exponentials, sine, cosine, continuous. Okay. Now, I don't even know if that's. Let's see these examples. Some beast examples we got going on here. All right. I'm gonna sketch this out for you guys. So if you have an asymptote, kind of like this, right? If you have an asymptote going on, you have this, and you have a value, right? Let's say this value is -3, right? This limit clearly doesn't exist because the left hand isn't equal to the right hand limit, right? If you can see, make sure I'm not blocking the board. Right, if you have an asymptote on one side and a point on the other side, clearly the limit does not exist. Let's check that out. If there's a hole in the graph, like this is 3, right? Value of f of 3 doesn't exist either. And then so sometimes a limit might exist, but the value of the function at that point isn't equal to the limit, which makes it not continuous. Okay? Let's talk about types of discontinuity. So there's 3 types of discontinuity that we're going to be covering in this course. I believe it's 3. So the first one, so we're talking about discontinuity. The one is if the limits of f of x as x approaches a exists, but limit of f of x as x approaches a does not equal f of a. So we call a removable discontinuity. It's removable. Removable discontinuity. Okay? That's like this. I'm going to erase this so you can see what's going on. Like my erasers. So if we have this, right? We have a hole right there, we have a point, right? So we can remove it. Now, if both limit as x approaches a from the left, f of x, and limit as x approaches a from the right of f of x, right, exists, and are finite, but don't equal, therefore jump discontinuity. Jump discontinuity. So this was the first one, this is the second one. So they're finite but not equal. So you have something like here, and then you have something here, right? So that's a jump right there. Okay? It's a jump right there. Then, as you get those down, let's clear up the whiteboard. If a limit as x approaches a from the left of f of x equals plus or minus infinity, or the limit as x approaches a to the right of f of x equals plus or minus infinity, then that is infinite discontinuity. Infinite. So let me draw you a sketch for the right. I'm just looking at some examples. So whenever you see an asymptote that's infinite, if you see jump discontinuities when there's a value and then there's a different kind of hole in a different space. Let's see, f of 3. F of 3. There's just singly a hole that you see and you can remove it, and that's what we call a removable discontinuity. And the x equals 4 is also a removable discontinuity. Yep. So that really covers discontinuities. I want to see what's the next lecture. Rates of change is the next lecture, guys. We're going to be focusing on that. Stay tuned.